Hi everybody. In this video, we are going to talk about how to find the components of a vector if we know the magnitude of the vector and we know the direction angle of the vector. So over here, I have a unit circle, and you can see that this vector over here extends beyond the border of the circle. So this vector is 3 has a magnitude of 3, okay? So we'll say that it's 1 unit from here to here, and this vector is 3 times longer than that. So this vector has a magnitude of 3 and a direction angle of 157 degrees, okay? Now, our goal is going to be to figure out the components of this vector. So what is the horizontal component of the vector and what is the vertical component of the vector? I didn't draw those very well, but you get the idea. Okay, now to do that, we're going to start off by focusing our attention on this vector over here. This vector is a unit vector. You can see that it is 1 unit long. And actually, I'm going to change this unit vector. I'm going to change the angle of the vector. I'm going to move it over here. So technically, this is a different unit vector than the one that I had before because the angle is different. But this vector is still a unit vector. It has a magnitude of 1, and the direction angle of this vector is the same as the direction angle of the vector that we were talking about to begin with. Now let's ask the question, what are the components of this unit vector? So this would be the horizontal component and this would be the vertical component. And figuring that out is actually very simple. It's just basic trigonometry. In order to figure out the horizontal component, all we would need to do is find the cosine of 157 degrees. Okay, and for that we would use a calculator. So I'm going to go over to desmos.com/scientific, and I'm just going to type in the cosine of 157 degrees, and that is negative 0.92 blah blah blah. I'm just going to round that to the nearest tenth, so we'll say it's about negative 0.9. And you can see that that does make sense from this picture over here because this horizontal component vector is moving to the left, so it makes sense that it is negative. And you can see that all of these are going up or down by tenths here. So this would be negative 0.1, negative 0.2, negative 0.3, and so on, 0.5, 0.6, 7, 8, 9. So this is, I maybe didn't draw the picture exactly right, but hopefully you can see from the picture that negative 0.9 seems reasonable for the horizontal component. Okay, now to find the vertical component, it's just as simple. We're just going to take the sine of 157 degrees. And again, we're going to do that in a calculator. So what is the sine of 157 degrees? That is 0.390 blah, blah, blah. So we're going to round that to 0.4. Okay, which also seems reasonable from the picture. Here's 0.5 over here. Okay, this is 1/10. It seems to be about 1/10 shorter than that. So 0.4 seems like a reasonable answer. Okay, really I should be saying approximately because we did round here. Okay, so the components of this unit vector over here would simply be, in angle bracket notation, negative 0.9, 0.4, or with the ij notation, negative 0.9i plus 0.4j. Okay, so we're very close to done here. Now, let me ask you, let's see if you can figure this out. Pause the video after I ask the question. Is this a true statement? Since this vector, the blue one, is 3 times longer than the unit vector, is it true to say that the components of the long vector would also be 3 times as long as the components of the unit vector? So pause the video, maybe rewind if you want to hear the question again, and think about it. The answer is yes. If the magnitude is 3 times longer, then the components, each component would also be 3 times longer. So if I know that the components of this vector are negative 0.9 for the horizontal component and 0.4 for the vertical component, I can just multiply these numbers by 3 in order to figure out the horizontal and vertical components of this vector over here. And that follows from what we were saying in a previous video. You may recall we said that if we have some vector and the components of the vector are x, y, we'll say x is the horizontal component and y is the vertical component, then if we multiply the vector by some number a, where a is just some scalar, it's just some number, then the components of the vector would also get multiplied by a. So the new components of vector AV would be AX for the horizontal component and AY for the vertical component. And it works vice versa also. If you multiply the components by some number A, then the vector itself would get multiplied by the same number A. Okay, so if we make this 3 times longer, then the components would be 3 times as much. So what is negative 0.9 times 3? That would be negative 2.7. And what is 0.4 times 3? That would be 1.2. So it's as simple as that. These would be the components of this vector. The blue vector. Let me just erase the green one here so you can remember that the blue vector really just does start from here. So that means that this horizontal component is moving to the left. We can see this is negative, and the length of it, or the magnitude, is 2.7. And the vertical component is moving up. You can see that this is positive, and the magnitude is 1.2. It's 1.2 units long. Right? In ij notation, we can write negative 2.7i plus 1.2j. So generally speaking, here's the rule. When we know the magnitude and direction angle of a vector, we can find the horizontal component by multiplying the magnitude by the cosine of the angle, and we can find the vertical component by multiplying the magnitude by the sine of the angle. Okay, horizontal component equals the magnitude of the vector, how long it is, times the cosine of the direction angle. And the vertical component is the magnitude of the vector times the sine of the direction angle. And just to recap, this rule works because cosine theta and sine theta are just the components of a unit vector, a vector that has a magnitude of 1 and a direction angle of theta. Okay, any vector which has a magnitude, let's say, of 3, like in the example that we just did, would be 3 times longer than the unit vector. So if these are the components of the unit vector, then we would have to multiply them by 3 to find the components of the vector that we're talking about. Or if the magnitude of a vector is 5, then first we would find the cosine and the sine of the direction angle, and that would tell us the components of a unit vector, a vector of length 1 that's moving in the same direction. But then we would have to multiply those components by 5 because 5 is 5 times more than 1. So we multiply it by however many times longer it is than the unit vector. There is another way to come up with this rule over here. If we imagine a vector, and let's call that vector v, and then we draw the components of that vector, then what we have here is a right triangle, and let's go ahead and call this angle over here theta. Then we know, based on the definitions of sine and cosine, which are based on right triangles, that the sine of angle theta is equal to the opposite side, which would be this one, over the hypotenuse, which would be this. And the cosine of theta would be equal to the adjacent side over the hypotenuse. But we can see from this diagram here that the opposite side is really just the vertical component of the vector. The opposite side here, opposite to this angle, is the vertical component of this vector. So I'm going to put VERT as my abbreviation for the vertical component. And we can see that the adjacent side over here is the horizontal component of the vector. And we can also see that the hypotenuse of the vector is, or the length of the hypotenuse is just the magnitude of the vector itself. So we can replace the hypotenuse there with the magnitude of vector v. And then if we just multiply both sides of both of these equations by the magnitude of v, okay, these cancel over here, and then we would see that the vertical component is equal to the magnitude of the vector times the sine of this angle over here, which is exactly what we said back here. And we could do the same thing for this equation. If we were to multiply both sides by the magnitude of v, then it would cancel over here, and we would get that the horizontal component is equal to the magnitude of vector v times the cosine of the angle, which is exactly what we said over here. Okay, so that's another way to come up with these rules. The reason I didn't start off with this proof over here is because this proof is based on the right triangle definitions of sine and cosine rather than the unit circle definitions. So that means that this proof is only applicable when the angle theta is greater than 0 degrees or less than 90 degrees, if you remember back from the trigonometry videos. Whereas the proof that we went through back up here, where we use the unit circle, that is applicable for any angle measure whatsoever. All right, but really it amounts to the same thing. This is the rule no matter what the angle measure is. Okay, so I think I'm going to end the video there, and have a great day.